Okay, we're going to start, folks. Good morning, everyone. I hope you are all settled with your teams so far. If not, if you still don't have a team, please go to Professor Chong in one of the tutorial time slots today or tomorrow. Okay, so we're going to continue talking about Milestone 1. Last lecture, we basically covered some of the APIs that we provide you that you will use to complete the functions that you need to implement. Today we're going to talk about one of the functions and how and we will brainstorm together on how to tackle that function. Okay, so just to recap what you expect from Milestone 1, we provide you with a read-only file that you cannot change called m1.h. m1.h basically has a list of functions with comments that tells you what you basically need to do to get that function to work. And some of them will show you also that they have some speed requirement that we'll go over in a bit. So your job is to basically write one or several CPP files in your mapper directory to basically implement those functions, and then you will need to pass some of the tests through ECE297 exercise. Okay? So we're going to cover unit tests in a lecture or two, but basically ECE297 exercise gives you the ability to test or hook to your executables or to your code and test some of the functionalities of your code. Okay, they give the detailed specifications of what do you expect from functionality, and they can usually test for is the function doing what it's supposed to do, is it meeting the speed requirement that we set for it. Okay, and there is also one test that runs Valgrind just to make sure that you don't have any memory leaks. So all the details are in the Milestone 1 handout. If you haven't started reading it, I recommend start reading it now and read it carefully because it has all the details that you need to complete the milestone and get the full mark. I encourage you to start as early as possible because there is a lot of technical knowledge that you need to build to complete the milestone. So you won't be able to start to finish it in time if you wait until the last week. Okay, so if you look at m1.h, basically you will see several functions, and you will see several functions like this. For example, this is called find street segment of intersection. And the comment above it basically tells you what it needs to do. So in this case, it tells you that returns the street segments of the given intersection. You are given an intersection index, and you need to return all the street segments connected to it. There is also another comment that says that the speed requirement of this function is, whoops, I don't see my marker, just a second. Yeah, the speed requirement here is high. So what does this mean? If you look at the top of m1.h, we define for you what high or moderate means. So in this case, if you read here, it says, oops, I hear my voice. Yeah. That this function must be very fast and likely to require the creation of data structures that allow you to rapidly return the right data rather than always going to the street database API. So you basically need to do some work in advance, store some of the data that you might need later on when you call these functions, and then quickly query these data once you call that function. And we've basically set our speed requirements in a way that if you go with the usual approach without storing any data, you will probably fail the performance test. You will pass functionality, but you will fail the performance test. Okay, sorry, just a second. And this function in particular, if you go to the tutorials this week, we basically covered it in detail and how to implement it, just to give you an idea what to expect from the rest of the functions and how to tackle these. So if you get this function wrong, that means either you didn't attend the tutorial or you basically cannot transcribe and copy the code from the tutorial. So this is basically giving you a freebie that we implemented this for you. Okay, so basically ECE297 exercise will, once you call it on Milestone 1, it will list several of these tests, and it will tell you what each test does. Some of them test functionality, and they have the name, the keyword func in their name, and some of them will test performance. Okay, They are color coded, so if you pass all the tests, you should see everything passes here in green. If not, it will show in red. So, as I said earlier, some of these tests basically check for performance, but how do we set these performance targets? Usually in a generic application, we usually look at the user experience, whether it is seamless to the user and everything is running smoothly, like in a gaming application, for example. But when you build APIs like this, which are low level, we don't have enough user experience to judge whether this speed is good or not. So what we usually target is basically trying to achieve the lowest big O notation on the functions that matter the most. What do I mean by the functions that matter the most? We know from, as course developers, that in later milestones, there are several functions that you might need to complete the other milestones. So we want you we want your application at the end to be smooth, and that's why we basically set high speed requirements on these methods or functions. We have our own reference solution that we built a fairly good solution for, and we set the speed requirements based on the running time of our own solution. We didn't micro-optimize it, so there are ways to improve it, but we don't care. We just want you to basically achieve the best O notation on each function that we care about. And the speed requirement that we set is basically around 2.5x what we achieved on those tests. So it's basically giving you some leeway in order to pass those tests. Okay, so let's talk about some of these functions and what to expect. What would you mean by the lowest big O notation? So for example, in load map, you have to load the data. There is no matter what, you basically have to go over all the data in order to store them. So the lowest possible performance on this function is O of n. N here basically the number of intersections. You have to at least go over all the number of intersections in the city, store them somehow. You can do whatever you want with them, but you basically cannot achieve less than that. Okay, so to achieve the performance targets, we believe that you have to choose the right data structure that you should use for each of these functions and where to store the data. So that's why it was very important that we introduced you to the STL libraries, because you're going to use them heavily in this milestone in the first two tutorials. So if you haven't attended those tutorials, please go watch the recordings. They are very important. Okay, so as I said, we will cover unit tests in a lecture or two, but this is just to give you the basic idea so that you can start coding what the unit test looks like. Each unit test will hook to your code by calling first load map here. So here we are calling load map on Toronto, Canada, for example. And at the end of the unit test, you will notice that we also close the map to basically close all the data structures that you called, that you implemented, okay? And then between those two lines, we basically call several of the functions that you implemented and that are listed in m1.h. So for example, here we are calling the find closest intersection on a variable called myPosition. We define this myPosition. It can be any random number, any randomly generated position. And we ran this on our reference solutions beforehand, so we know what the actual answer is. So in this case, the answer should be 22,333. Okay, so we check the output of your function whether it is equal to that number or not. If it is not, that means there is a test failing, and we will report what test failed for you. Okay, if it passes, then you will not see any error, and it will basically go to the next test case. All of the public test cases are listed under the public directory. If you that directory is listed in the handout, and if you go to those files, you will basically see all of the test cases that you will be tested against. Remember that these are only the public ones. There might be private ones that we will run after you submit your code. This is to make sure that you didn't hard code any of these numbers, for example, in your code, or you covered all the corner cases that are listed in the handout. Okay, so the first thing, again, we call load map. But what should we do in load map? The comment above it says basically we have to load anything you want here. So what does this mean? There are two approaches to this, okay? One is just load the map by calling the lower level API function that loads that map. For example, in Street Database API, it's called load street database, and you will pass to it the path to the file that you want to load, okay? And then basically you will implement all your higher level API functions, which are listed in the M1 handout, by calling the lower API levels over and over in each single function. The good thing about this is that it's called stateless. What do you mean by stateless? Stateless means that we don't store anything. We implement what we want and return the answer directly to what questions we asked immediately once we call the function. We don't store anything beforehand. The advantage about this is that it's very easy to debug. If there is an issue in one of the functions, we know where to go and we know where the bug might be. But the problem is that it's going to be too slow. We won't be able to keep looping over and over, or for example, over all intersections in order to quickly get one of the answers that we want. So the other approach, which is the one we recommend you to do in order to achieve the performance targets of this milestone, is to create some new data structures. These data structures are up to you, but you basically need to think about it and choose the best data structure that can achieve the lowest performance for your certain functions, okay? Then if you use these data structures, you would basically store these data beforehand. And in this case, basically you load them in load map. And then once you call those those high-level APIs, the ones that you are implementing, you would just go and get the data that you want from that data structure quickly. Okay? Any questions so far? Nope. Okay. Oh, C05. Was that on purpose or no? Okay. Sorry, what? Yeah. Okay, but our suggestion, okay, now that we know the two approaches to work, to what to do in load map, our suggestion is try to follow an agile approach when it comes to software development. I usually follow that approach even at my work. I get something simple working first, make sure that it works and achieves at least the functionality or robustness that that I expect, and then I worry about the performance. Once I look at, okay, now my function, I know what my function is doing, I can talk about performance and let's think about how to optimize it. In this way, actually, you will probably notice that whatever you implemented inside the function to meet the functionality, you will again use it. You won't actually throw it away, but you will just move it around your code and probably put it in load map. So basically, even if you are not able to achieve the performance target of all the functions, you at least guarantee that you are meeting the functionality. So you start by getting, let's say, half the mark, and then one by one you basically achieve the rest. But remember, I'm saying that you can store as many as you want in load map, but remember that load map is still speed tested. It's a bit loose, but basically we want to make sure that you are not doing something crazy in it. So if you, for example, Toronto has around 250,000 intersections, okay? If you're doing something in the order of n squared, that's gonna be a very large number. It might take hours to finish, and so you'll probably fail the test for that. But we gave you a runtime or a performance target that basically works with anything that is O of n or O of n log n. So if you are doing storing data structures in that range, then you should be fine. Okay. Again, I highly recommend that you go to the tutorial this week if you haven't done yet, because we will cover one of the functions in detail and how to tackle it and what kind of data structure that we need to use to basically achieve the performance target. Now, today I'm going to basically brainstorm with you another of these functions, but we're going to talk high level. We won't code anything. We just want to basically think together what kind of data structure is suitable for this. So we will talk about the find intersections of a street. So if you remember from last lectures, the street database API basically consists of 5 different entities: intersections, street segments, streets, points of interest and features. Okay, so this function tells us basically I am given a street ID, a random street ID, and I want to basically return all the intersection indices that basically span through this street. So what do we know from the street database API? We know that if we have a street segment, not a street, if we have a street segment, we can get its basically to and from intersections, and we can get what street ID it is part of. The problem with the lower level API is that street cannot answer questions about intersections. So basically, we cannot tell the street database API, get this street ID and give me the intersections. Otherwise, basically, the implementation of this function would be easy. Okay? So, for example, this young street, it consists of several of these intersections, and we basically want to return them all in a here STD vector. Okay? But again, we can't do that by calling the street immediately, so we have to go through the street segments. So each street segment has the ability to give you its to and from intersection, and from that you basically have an idea how to tackle this. Okay, so we are going to basically, I'm going to give you some time now to think with your group and brainstorm how to tackle this function. Don't worry about performance yet. We want the simple approach first. As I said, I recommend basically going with the simplest approach first. And later on, we'll basically talk about how we optimize it. Before we start, basically, remember, I'm gonna give you some pointers what street database API can give you. It can give you first the number of street segments in the city, okay? That might be useful to you. It can give you if you have the street segment index that you want, it can give you a struct of the street segment info. So basically, this street segment info contains the intersection index and the street index it belongs to. Okay? So using these functions, try to think about how to tackle that function. Remember, we just want to return all the intersection indices that cover the street segment, the street ID that we are given. Okay? So we won't write the code. It's just like a pseudocode. I want you to give me a description of what basically the code should look like. Like there is a for loop here, there's a if statement there, whatever, and what on a high level what we are doing. So I'll give you some time here. Let's see. Yep. Okay. I'll go over and ask you questions, and once the time is finished, basically we can talk. We can discuss it at large. Okay, so I heard some good suggestions out there. Now I'm going to pick on some of you to give me an answer, unless someone wants to volunteer and give me an idea of how to solve this function. Let's try with a chocolate bar. Anyone wants a chocolate bar? No? Okay, D09, I'm gonna pick on you. Yeah, can you speak in the microphone, please?
All right, so I would just, okay, so you're in a street and then you can get the number of street segments and then you can loop through all these street segments.
Sorry, you gotta speak louder, I can't hear you.
Sorry, this is the mic?
Yeah.
Oh, yeah, sorry. So you have a street index.
Okay.
And then you have to get the number of street segments in that street. And then you, for each of these segments, you loop through them and then you return those intersections. And then you also have to compare the street index so that you don't get off that street. Yeah.
Okay, so basically you're saying that if we loop over all the street segments in the city and then compare whatever, and then get the street segment info of each street segment, we can know the street ID that it is part of, right?
Yeah.
And then once we know that, we know the to and from intersections that are connected to that street segment. There is only one problem though. Can anyone figure it out? Basically, if you keep getting the from and to intersections from each street segment, you will probably end up having duplicates. So you just need, oops, did you have the answer? Yeah, sorry. So you will probably have to think about how to avoid those duplicates somehow.
Oh, yeah. I think you can once you're looping through it, you can compare your old maybe like intersection index and your new ones.
Yeah, so whatever you stored already, you just make sure that you don't store it again.
Yeah.
And we need some smart data structures to actually be able to do that quickly, right? So that's one thing we need to worry about. Thank you. Okay, so I'm not gonna write the code. I'm basically, this is what your friend suggested here. Basically, we are looping over all the street segments in the city, okay? At the top of the function, first of all, we need to define the function that we need to return. So at the bare minimum, we at least need to define an empty vector of all the intersection IDs that we want. And at the end of the function, we basically need to return that vector. Now we need to populate it, or we need to fill it up with data. So we loop over all of the street segments. And then for each street segment index, remember that the street segments indices go from 0 to whatever number of street segments minus 1 in the city. So we loop over them one by one. We get the street segment and info associated with that street segment. And then if the street segment info dot street ID, remember that the lower level API gives us that ability to know which street ID it is part of. If it is equal to the one that we are given here at the top, then we basically go ahead and add the to and from intersections one by one and just make sure that we avoid duplicates. Okay, so now let's think about performance. Anyone know the time complexity of this in terms of number of street segments, like a big O notation of this? D10, do you have an answer or no? Yeah. Sorry, can you speak louder?
Is it O of n?
Yes, it is O of n. Basically, we are looping over all the number of intersections, street segments in the city in order to get the answer that we want. Now, a street usually has like around a dozen intersections on it. And here we are basically looping over all of the street segments, which is around for example, in Toronto, it's around 190,000, right? So we are wasting a lot of time just to get the answer that we want. And that's why we're saying that we cannot keep doing this every time we call the function. We need to store this data somehow outside the function and quickly query the data that we want. Okay, so that's what we mean by we're going to use the same code, but moving it to the load map function. and store it in some smart data structure in order to give that answer to every single street in the city. Okay? So basically, we loop over all the street IDs in the city, in the inside load map, and we repeat whatever we did in the previous slide, basically going over all the street segments and store the intersections connected to that street ID, right? You just need to make sure that you don't loop twice, basically by keeping track of whatever street ID that you visited already. And so the fastest, in this case, if you store the intersection indices inside load map for every street, when you call the function find intersections of the street, basically the fastest way possible that you're going to achieve this is you just return the answer directly from the data structure that you built. And this is usually O of whatever number of intersections on the street, which is usually around a dozen or 15 intersections. Okay, does that make sense? Feel free to ask any questions. This is new anyway. Okay. So remember in the unit test that we showed, basically we first load the map and then we hook function calls to your APIs by basically calling each of the functions one by one. And then at the end we close the map. Why do we do this though? So basically, because we run the tests one by one, and you are building some data structures inside your load map, we need to make sure that you erase the data that you've built inside closed map. Otherwise, you'll basically, your memory usage will blow up if you keep calling these functions one by one, and if you keep calling a unit test after a unit test. To make sure that you are actually doing that, we have a Valgrind unit test that will just run Valgrind and make sure that there are no memory leaks and that basically your memory usage is reasonable. Okay? So remember, you must free all the memory that you've created inside load map by deleting everything inside closed map. Otherwise, you'll probably lose marks because we will test against this. The problem though is that with memory checking, if you remember from the previous, from your handouts of Milestone 0, that running with Valgrind can make the program really slow. It's probably 10 times slower. So we cannot do this when we are running a submission test or we're running an exerciser test on a city like Toronto, because Toronto is very big, and if we're running 10x slower, basically the test will never end. Or it's going to take a lot of time. So to this end, basically, we test Valgrind on a very small city called St. Helena. Basically, it's a very small city in the middle of the Atlantic Ocean, in the middle of the South Atlantic Ocean, that has like less than 100 streets probably. And running Valgrind on it, we basically check that if you are clearing the memory properly or not. And we will basically be able to do that even with Valgrind because the city is small. Fun fact, this St. Helena is where Napoleon was basically banished in later years of his life, after they captured him. Okay. So one thing we note here is that inside the unit test, we only call load map on the street file that we want to load. But the problem is, we know that we've basically stored some data inside load map in order to query them later. How do we get this data here if we don't pass any parameters from load map to your function? Remember, you cannot edit the header file. We cannot add parameters, or we cannot remove parameters from the functions. So how do we make sure that the functions that you are calling basically get the data that you've defined earlier without passing those data? Okay, the answer to this is global variables. You'll probably say that, oh, I've been told that using global variables is bad. But that's true. If you overuse them, probably it is bad because your function, reading it first is gonna make it difficult, and it's very error prone. If you use a lot of global variables and you keep changing them, basically you'll end up with a lot of bugs. But almost every single program will have some global variable defined somehow in order to basically store data for a long time. So for example, if you use cout or cin, which are basically how you input or output things on the terminal. These are actually global variables defined under the STD. So even though they are widely used, they are still global variables to make it easier for the user to use them. Okay? But you can be smart enough and limit them somehow. So instead of defining, like, let's say, 10 or 20 global data structures to store every single data that you want, you can group this similar data structures together under certain classes. So for example, if I have multiple data structures that would query based on the intersection index, I would create a data structure and store all of these new data structure. I'll create a new class and store all of these data structure inside that class. So I can call it, for example, street graph, and then organize the data and avoid lots of basically global variables. So once we call the load map, we are creating this street graph. You can call it whatever you want. You can do whatever you want. And then with this street graph, it's global. It's known to the whole program. So even the unit test can basically have access to it and have access to that data. So once you call that function in the unit test, basically we know that we're going to get the right data that you loaded. Okay. One thing to be smart about with global variables is, in order to avoid a lot of bugs when using them, we make sure that they are only changed in one function of the program, okay? So in this case, basically, we are only going to write to that data structure or that global variable inside load map in order to store the data that we want from the lower level APIs. And in all of the other functions, when we use them, we are just basically asking them questions and reading whatever data is inside them. So we only read global variables inside the function, and we only change the global variable inside load map and also close map, because in close map we are basically deleting that data structure. So before I go here, any questions so far? I hope this gives you an idea of how to tackle some of these functions in M1. And the last thing I wanted to talk about is, so one of the functions in the Milestone 1 handout is you have to find the feature area of any random feature in the city. If you remember from the previous lecture, these features are represented as a collection of points that are stored in order, one by one. And if it's a closed feature like this, like High Park, for example, then the first point is basically going to be the same as the endpoint in the list of points. If it's a triangle or a square, it's very easy to find its area. But if it's a polygon, it might be tricky. Anyone knows, so you need to do some computational geometry here. Anyone knows how to find the area of a random polygon mathematically? Yes, ECE297.
I guess cut it into triangles.
Sorry?
Cut them into triangles.
Yeah. So the easy way to do this is to cut the polygon into triangles and find the area of each triangle. Mathematically, that's very easy to do. Unfortunately, programmatically, it's very complicated to actually cut a random polygon into basically triangles. So it's a good solution, but probably can't do that in this course. Any other solution? Anyone can think of how to do this? It's okay if you don't know. This is probably tricky. Okay, so we do this with something called numerical integration. It might sound fancy or complicated, but it's actually not that fancy. So each of the polygons, as I said, is guaranteed to have the list of points in order. That means that we go from one point to the next, to the closest neighboring one. And there are no holes inside the polygons, okay? So we are guaranteed that the polygon is closed from the inside. With these two constraints, we can do something like this. Basically, we can divide the polygon into a set of trapezoids, and using the area of a trapezoid, we can track that one by one. What do I mean by that? So we start by having y1 and y2 as these 2 points here, and then we define the trapezoid to be all of the area connected to the y-axis, okay? Even the ones that are outside the polygon. I'm gonna talk a bit why we do that, okay? So, since y2 is greater than y1 in this case, the net area here is positive. When you do y2 minus y1 times x2 plus x1 over 2, this is positive, right? So we do that once, and then because we know that the points are ordered, the next point that we're going to go to, for example, is going to be this point here. So y2 in this case will become the one above, and y1 will be the one that we've already used. Again, you add that to the target, to the area that you achieved, so that's all positive. And you keep doing this one by looping over all the points, okay? So in this case, y2 is this one, and y1 is this one, and then until we get to that upper point, right? So we've added all of these area. Now the problem if we stop here is that basically we've included all of the area outside of the polygon that we want to achieve, right? We want to calculate. So we continue doing that with the rest of points, but now notice what's gonna happen. Once we get to the next point, now in this case, y2 is smaller than y1. So if you follow the equation here, y2 minus y1 is going to be negative. So when you add it to the total area that you have achieved, you're basically deleting the area that is outside the polygon, okay? So anything in red is now a negative and basically will be subtracted from the total area that we found. And then until we reach the last point, so we basically deleted all of this outside and we just found the result that we have right now is basically the area of the polygon that we want. And how do we know when to stop? Basically, if we reach to a point where the last point is equal to the first point, that means we've covered all of the points. Any questions on this? Yes? Sorry, just a second. Yeah. Oh, you don't have a microphone, right?
What if there is a concave point, like it has some?
Yeah, that's a good question. What if it's a concave polygon? Well, we won't give you that. We are guaranteeing you that it's a closed polygon with no holes inside it, and the points are ordered in order, right? Otherwise, it's going to be more complicated than that to calculate the area. Any other questions? If not, basically, this is it for what I have today. We'll have 5 minutes left. I can stay here and answer any questions if you want. If not, thank you for attending.
Good. Yeah, I'm doing great. No, I'm encroaching on your area. I'm just trying to get set up quick. No rush. This would be an easy one. I don't think.
Yeah, I went through it. No activities or
But
anything.
yeah, last lecture I didn't get through everything that I wanted,
Oh,
so
okay.
I had to sort of chop this one up.
Okay. How was the last lecture?
I mean, it was good. There was lots of questions about mitochondria.
Okay.
Maybe in future years I just need to introduce it. I don't need to know.
Talk too much details about it.
They want to know all the details.
That's the thing. It's like with the survey and everything, no one's actually interested in biology, but then they ask all those questions, and you're like, oh, if I answer, then we're
They're going to like